Today we shall study about the critical pressure ratio for maximum discharge through a nozzle, and also shape of nozzle for getting uniform pressure drop. First, shape of nozzle for a uniform pressure drop. A convergent divergent nozzle is shown in the figure. The initial pressure of the steam is say 10 bar and final back pressure of the steam is 10 bar or is 1 bar. The expansion of steam takes place from 10 bar to 1 bar. Now we want to find out what is the shape of the nozzle for getting uniform pressure drop throughout the nozzle. So here we will find out the shape of the nozzle or area of cross sectional area AC at all the sections for uniform or for unit mass flow rate. Let us assume m equal to 1 kg per second. Now the back pressure is the base of the graph is shown here. It shows discharge velocity and specific volume versus the pressure ratio. So then the base of the graph shows the back pressure. The space of the graph is graduated uniformly for getting uniform pressure drop. See, it is graduated as 10 bar is the initial pressure, 10, 9, 8, 7, 6, 5, 4, so on up to 1 pressure. So here you can see m equal to, what is m equal to? A2C2 by V2. M equal to A2C2 by V2. So if m equal to 1, then A2 equal to V2 by C2, where V2 is the specific volume, C2 is CZ is the AZ is equal to VZ by CZ. VZ is specific volume at any section, CZ is velocity at any section. So velocity at any section of the nozzle is found out by knowing the pressure at that section, assuming isentropic expansion. We can, if you know the pressure at any section, assuming isentropic expansion, we can find out the enthalpy at that section. Then velocity of the steam at that section equal to CZ equal to 44.72 root of H1 minus Hz, where Hz is the enthalpy at that section. Then specific volume is also found out at that section, Vz, small vz, by knowing the condition of the steam at that section corresponding to the pressure at that section. So by knowing the velocity and specific volume, we can find out the area at any section. Az is equal to Vz by small vz divided by capital CZ. Then similarly we can find out the area at all the other sections. The variation of velocity, specific volume and discharge is shown with respect to pressure ratio. It is found that both velocity and specific volume increases with respect to pressure ratio, and specific volume increases rapidly at the end of the nozzle. And discharge, it is found that discharge increases up to a certain value of pressure ratio and then it decreases and becomes 0. So the area of the throat, the area having the minimum cross section area is known as throat, and we found that discharge will be maximum at the throat. Area will be minimum and discharge will be maximum at the throat. Now we will find out mass of discharge through the nozzle. So expansion of the steam is shown, assuming isentropic reversible adiabatic expansion from P1 to P1, P2, 1 to 2, following the law of PV raised to n equal to constant. Then we know that what is the mass flow rate of the steam flowing through the nozzle by continuity equation, m equal to A2C2 divided by small v2. M equal to A2C2 by small v2. This is equation number 1. Now we know that in the pressure the expansion work done in the nozzle, the expansion of the steam taking place in the nozzle is converted into kinetic energy. So T2 C2 square minus C1 square by 2 equal to integration of P1 to P2 VdP. This is the integration of P2 to P1 VdP equal to expansion work. Then the expansion work P2 to we know that what is the expansion of the steam follows the law PV raised to n equal to constant, or V equal to C by P raised to 1 by n, or V equal to C by P raised to 1 by n. So integration of P2 to P1 VdP equal to C raised to 1 by n P raised to minus 1 by n dP. So this case integration of this will give work done, expansion work done, it gives P2 to P1 VdP equal to n by n minus 1 P1 V1 minus P2 V2. Expansion work equal to P2 to P1 VdP equal to n by n minus 1 P1 V1 minus P2 V2. Now equating this, gain in kinetic energy equal to C2 square minus C1 square by 2 equal to n by n minus 1 P1 V1 minus P2 V2. Then C2 equal to, neglecting the initial kinetic energy C1, then C2 is equal to root 2 n by n minus 1 P1 V1 minus P2 V2. And taking P1 V1 outside, we will get 2 by n minus 1 root of 2 n by n minus 1 P1 V1 1 minus P2 by P1 raised to n minus 1 by n. This is the equation for the velocity C2. Then we have P1 V1 raised to n equal to P2 V2 raised to n. Therefore, V2 equal to V1 P2 by P1 raised to minus 1 by n. Equation number 6. Substituting the value of C2 and V2 from 5 and 6 in this equation 1, m equal to A2 C2 by V2, then get the value of mass flow rate through the nozzle. M equal to A2 divided by V1 P1 V2 by P1 raised to minus 1 by n root of 2 n by n minus 1 P1 V1 1 minus P2 by P1 raised to n minus 1 by n. It gives m equal to A2 2 n by n minus 1 P1 by V1 root of P2 by P1 raised to 2 by n minus P2 by P1 raised to n plus 1 by n. This gives the expression for the mass flow rate through the nozzle. Now, throat pressure for maximum discharge or existence of a critical pressure ratio for maximum discharge. So, expression for the mass flow rate is shown here. Already this has been derived just now. M by A2 equal to root 2 by n by n minus 1 P1 by V1 P2 by P1 raised to 2 by n minus P2 by P1 raised to n plus 1 by n. Now we see that already you have discussed that the discharge increases with respect to with the pressure ratio, then up to some value of pressure ratio, and then it becomes maximum at certain value of pressure ratio, and then it decreases. So you know that area is minimum at the throat and discharge will be maximum at the throat where the area will be minimum. Therefore, the pressure ratio at which the discharge is maximum is known as a throat pressure is known as a critical pressure ratio. So we will find out the value, what is the value of critical pressure ratio. So here in the expression for mass flow rate, we will see that P1 V1 are the initial condition of steam, that is constant, and n is the index of expansion, also it is constant. The only variable is P2 by P1 pressure ratio. Therefore, for getting maximum discharge through the nozzle, differentiating this term m by A2, differentiating the term in the square bracket, that is P2 by P1 raised to 2 by n minus P2 by P1 raised to n plus 1 by n with respect to pressure ratio and equating it to 0. So we are differentiating this, the term in the bracket P2 by P1 raised to 2 by n minus P2 by P1 raised to n plus 1 by n with respect to P2 by P1, that is pressure ratio, and equating it to 0. So equating it to 0, putting the value of P2 by P1 as R, we will get d by dr of R raised to 2 by n minus R raised to n plus 1 by n equal to 0. So you will get R equal to P2 by P1 equal to Pc by P1 equal to 2 by n plus 1 raised to n by n minus 1. R equal to P2 by P1 equal to Pc by P1 equal to 2 by n plus 1 raised to n by n minus 1. This is the value of critical pressure ratio for getting maximum discharge. So then for critical, we will get the critical pressure ratio for different condition of steam. For example, for saturated steam, n is equal to, taking n equal to 1.135, critical pressure ratio will be equal to R equal to P2 by P1 equal to Pc by P1 equal to 2 by 2.135 raised to 1.35 divided by 0.135 equal to 0.58. For superheated steam, n equal to 1.3, we will get R equal to P2 by P1 equal to Pc by P1 equal to 0.545. For wet steam also, we will get, substitute n equal to 1.035 plus 0.1x. For gases, n should be replaced by gamma. So R equal to P2 by P1 equal to Pc by P1 equal to 2 by gamma plus 1 raised to gamma by gamma minus 1. It will get 0.5 to 8. Thus, we have found out the value of throat pressure. We have derived the expression for the throat pressure for getting critical pressure ratio for getting maximum discharge to the nozzle. Then we want maximum discharge. For getting maximum discharge, substitute the value of critical pressure ratio in the expression for mass flow rate. You will get the maximum discharge. Max equal to 0.635596 P2 A2 root P1 by A1 for initial separated steam, initially dry saturated steam. For initially separated steam, Mmax equal to 0.66726 A2 root of P1 by V1 for initially separated steam. Also, we will define a critical temperature ratio. Just now we have defined a critical pressure ratio. We have also a critical temperature ratio. T2 by T1 equal to Tc by T1 raised to P2 by P1 raised to gamma minus 1 by gamma. So it will be P2 by P1 is already we have defined. What is P2 by P1? P2 by P1 is 2 by gamma plus 1 by gamma minus 1. We will get T2 by T1 critical temperature ratio equal to 2 by is equal to substitute value of P2 by P1 as the substitute value of critical pressure ratio here. We will get critical temperature ratio equal to 2 by gamma plus 1. This is for ideal gases. Critical temperature ratio for ideal gases equal to 2 by gamma plus 1. This is all about the critical pressure ratio for maximum discharge and maximum discharge through the nozzle. We will continue in the next class. Thank you.